Good morning. I'm interviewing an old friend, George McMahon, who started out with the Corps of Engineers and then went into private practice. George and I are both involved in the world of water resources modeling and planning. Um, and let me turn to George and ask him the most basic question. When somebody comes up to you at a party and says, "What do you do?" Can you tell me what you do professionally and how you would characterize your main involvement with modeling water systems?
That's a question I don't go to that many parties, so I guess I don't get asked that too much. But professionally, I basically have been involved in water resources engineering, uh, planning, design, construction, and operations throughout my career, which started with the Savannah District Corps in 1970. I had the good fortune while with the Corps to go through the complete cycle of planning and design, construction, operation of Richard B. Russell Dam, which is a 600 megawatt pump storage project on the Savannah River. So I got some really good experience doing that. That's probably not easily obtained nowadays. My modeling experience basically starting back in the early 70s. We actually were involved with physical models. We work with the Waterways Experiment Station to do physical modeling of, for example, spillways or hydraulic structures. We did some very early numerical modeling, hydrology, hydraulics, kind of physical process models, and got into some very early, I guess towards the mid 70s, got into some operational models, which are kind of a combination of the physical processes and operations decision support. And more recently, of course, we're moving to very sophisticated and powerful models, both operational and also integrated modeling platforms, things that platforms that integrate standalone physical process and decision support models and environmental socioeconomic impacts assessment. So it's kind of come to very comprehensive, essentially integrated modeling applications. You're muted, Bill.
Your work as it's changed through the years, can you kind of, from a high level view, tell me what the biggest changes in modeling water systems have been over the course of your professional life?
Well, I'm giving away my age, but it's a long story with 50 years in practice now. First of all, we models are commonly thought of today as computer software, but in the early 70s, before there were high-powered computers, models are really just the algorithms or the procedures used to represent a process or to solve a problem. And so again, like what we call today is models or software, which is sort of the amalgamation of many models and along with the inputs to their implementation. I would say conceptually, hydrologic models haven't changed all that much over my career. In other words, we're still doing the same rainfall runoff kind of modeling, unit hydrographs and hydrologic routing techniques and stuff that have been around for decades. Of course, the computer implementation and georeferencing of these things is much more sophisticated and powerful than it has been. Hydraulic models have changed quite a bit. Numerical solution techniques, we've got very high, much increased computing power, so we can do an awful lot with numerical models that we used to only be able to do with physical models previously, and also with we can do things with numerical models, and I'll talk a little bit later about some of the things we've been able to do with numerical modelings that would have been almost unimaginable, 50 years ago or so. likewise, operational models have become very capable by, they incorporate more complex physical process as well as very complex conditional operating rules that, were not around, 30, 40 years ago. Some of the early work we did when I started with the Corps, we actually were doing standard step backwater calculations using hydraulic slide rules and mechanical calculators, if you can imagine that. We'd have a technician come in and do maybe one cross section a day, backwater computation. And about, I don't know when it was, early 70s, 72 or 71 or so, we came up with the Corps came up with the first version of HEC2, which is the standard set backwater program. Was run on punch cards on a mainframe computer. The computer filled the whole room. From that there was HEC1, and then eventually there was HEC3, which was the first reservoir system model. They also ran on punch cards on mainframe computers, but eventually they were moved to PCs, PCs got increasingly more powerful, so these models also got more powerful. But the characteristic of these models, they were basically text input and output. Today, computers, PCs are extremely powerful, and of course now we have graphical user interfaces and dynamic displays and animations, that sort of thing. The biggest changes, I think, with computational capacity improvements, we now have capability of doing very detailed and rapid simulation of very complex systems, physical, operating rules, and coupling these models together, so that we have virtually limitless capabilities for trial and error attempts or at potential solutions. And we've expanded I would say, the solution space in water management as a result. The one thing that's, I guess, different a lot from today and the early, say, text-based model inputs was that is basically the models, the software and the data that run the software are relatively inseparable now. You can't look at just the inputs to an HEC RAS model, for example, or an HEC RESIN model. You have to look at it within the model itself. So you can't just send the input to somebody to evaluate outside of the software. So in some ways, there's a little bit less transparency, I guess, in viewing models and reviewing models and assessing their validity, reproducing these things. Yeah, go ahead, Bill.
That's an interesting twist on all the advances that you talked about. Looking back over those changes, do you see a trajectory that gives you expectations about what will happen in the next few years?
Yes. I mean, I'm not a very visionary futurist or anything like that, but it's clear that model integration is what's happening now, and there's a lot of developments within the Corps with HEC WAT, the watershed analysis tool, and HEC RTS, the real-time simulation, but also in other proprietary platforms and actually public domain platforms as well, like Delft Q's flood early warning system is another model integration platform. And these things are nice because they have kind of a plug and play capability where you can take models independently developed and basically incorporate them into a modeling framework so that these different models can talk to each other. So I think that's one area where things are going. Another thing is some of the work that NOAA is doing on the national water model implementation, basically for stream flow forecasting and simulation. And so it may be to the point where, hydrologic analysis may be something to be able to pull off the shelf, basically, or pull from a database, as opposed to having to, start it from scratch with each new river basin study.
Let me push you beyond just the next couple of years, and make me put that futurist hat on your head. If looking farther down the road, 10 or 20 years from now, how do you think, if we had this conversation in 2040, what would we be talking about?
That's a really tough one. I can't pretend to know what would happen, but I would. My guess is there's going to be something going on in artificial intelligence, and so I can see AI-driven, responses to queries, very detailed and specific queries, that there may not be any need for engineers to do anything. It may be just something like you can ask Siri, what would be the probable maximum flood at a given location or something, and it'll be able to come up with it.
Interesting.
Yeah, I actually hope not, because that kind of takes a lot of the fun out of things. But
indeed, and that raises the question. Now that you've talked about how your business and our business has evolved, how do you define success as a water resources modeler? When do you know that you've served your purpose?
That's a. I mean, there's a lot of things that sort of define success. First of all, the model has to be reasonably accurate and reproducible. I think that's kind of a given, but that's not nearly sufficient, because a model is successful if it can facilitate or aid in water management decision making, or resolution of water conflicts. If it can help lead to a successful resolution of water conflicts, would be a real measure of success. I think it's important that modelers and users of models have realistic expectations about model limitations, and the fact that all models are, as George Box, the statistician, said, all models are wrong, but some are useful. In the ACT-ACF negotiations, which you remember, Bill, there was a kind of a tacit recognition that we had very complicated, complex models, and then we wrote allocation formulas, kind of based. These models were used to represent allocation formulas, but of course, the language and the provisions of the allocation formulas are not the same as the model. The model makes perfect decisions with perfect information, whereas following a formula, or adhering to an agreement doesn't always work out that way. So that's another thing, is that models can give you information, but they're not the answer. And
so go ahead, finish.
I was just going to say, the only other thing is just transparency and the reproducibility of model results, so that you don't have, if there's stakeholders involved, you don't have concerns or disagreements over the validity of the models themselves.
So let me follow up and ask you a more specific question about modeling and water resources planning. Tell me what's the value of modeling? How does it fit into a planner's role? I'm more of a planner, you're more of a modeler. How do we work together in your mind?
Well, it's like, I guess, physicists would say that if the mathematicians knew what problems we had to solve, we could probably solve anything, but what the models can provide is quantitative information for comparative analysis of planning alternatives, in a search for what you call satisficing solutions, where you're looking for acceptable, not necessarily optimal, solutions to problems that are driven by water. Hopefully they're driven primarily by water because that's what the models that we're talking about address. But there's often proxy issues related to uses of water. And these proxy issues are, the bigger background social framework kind of thing that some of these are negotiable and some are not. And so there's a whole interesting study of what makes a conflict intractable versus something that can be resolved. And so basically, the thing that the models can help with is accurate description of the impacts of water projects or water management strategies on water availability, the water environment, and potentially socioeconomic, effects as well.
So modeling can't always solve problems because they're more complex. They include other things besides water. So give me an example from your life of the most successful real-world modeling exercise you were ever involved in. What did you do, and why do you think it was successful?
The most successful actually was, and it was because the surrounding issues weren't intractable, I guess I would classify it that way. The most successful model effort I was involved in was a simple spreadsheet model, basically, to look at storage reallocation and storage accounting procedures for Alatoona Reservoir in connection with two water supply users of Alatoona Reservoir. And at issue were things like how much storage had to be reallocated, how were return flows credited, or were they, if they should be credited at all, and how should they be credited, and how should inflows be apportioned. And so developed a spreadsheet that basically looked at 8 different accounting methods for apportioning reservoir inflows, withdrawals and return flows on water supply storage utilization. The Corps, I think, wisely chose to adopt the least impactful accounting method in its determination of reallocation requirements and subsequent storage accounting. And which was kind of a win-win for everybody, because the reservoir was going to be operated the same way. The same releases would have come out of Alatoona as would have come no matter what accounting system was used, because it's basically a virtual accounting system. And I think the reasons for success was the model was simple and verifiable. There was no inherent sources of intractability between the parties. The parties were the state of Georgia, 2 water utilities, and the Corps of Engineers. And again, like I said, the idea that the Corps didn't have any formal reallocation of storage accounting policies that required revision as account of this settlement, or as account of this agreement. So there was no, I guess, immovable objects, or in the way of a solution like this.
So you've told me about your success. I have to ask, what was the most unsuccessful application of a model that you can remember?
Well, it is one. It depends how you define success, but I would actually consider the one that you were also involved in, Bill, is the ACT-ACF water allocation negotiations.
Yep, I agree.
In the sense that they were not successful, in the sense that there was no negotiated settlement. And as a result, we had more than 15 years of litigation by the states against the U.S. Against the Corps, and then ultimately the Supreme Court case, Florida v. Georgia, on water allocation in the ACF Basin. And I think the reasons that were not successful were many, and I could only think of a few. One is that water in this case was really a proxy for much broader, more pervasive economic and political issues that were not amenable to resolution, were not really, some may not even been negotiable in the first place. And then there's a little bit of competing models. We had, in terms of reservoir system models, there are at least 4 that I know of that were involved: HEC5, and then Stella, and then an optimization model, ACF DSS, and then ultimately ResSim, HEC ResSim, which is the model that is now used to support real-time operations in both basins.
Okay, so you talked about 4 different models there. As a modeler, do you work with software developers in the practical application of their product? How important is that in the projects you've been involved in?
Yeah, it can be important. I guess the best example I can give is with HEC5. When HEC5 replaced HEC3, because HEC3 was a monthly model and it couldn't do flood control simulation. And I worked with Vern Bonner and Bill Eckert at HEC, and Richard Hayes at HEC. Basically, we wanted to do an analysis of the hydropower resource analysis of the Savannah River system, which had, remember, it had a Richard B. Russell pump storage project between 2 other conventional projects. And so worked with them to put in pump storage capabilities in HEC5 and system power capabilities. And the model was basically tailor-made for the Savannah system, but it was a great, it ended up working out real well. It actually helped us size the power plant for Richard B. Russell. It helped us develop the operating rules, the first water control manual, for the system. So it was a very good interaction. And also, I would say that HEC5 is still a very useful and powerful tool, even though it's a legacy model today. I still use it quite a bit because if there's a relatively simple set of operating rules, and georeferencing isn't really necessary. I find HEC5 to be a very, very useful tool. And I think at one time, Richard Hayes told me that it was the most used model within the Corps of Engineers. This was before the next generation models came out.
I believe it.
And then I was going to say another one was a case that we did recently with HEC RAS, the new version of HEC RAS. We were analyzing the effects of a bollard fence along the Rio Grande River and how much it might cause flow deflections. It was basically on the U.S. side of the Rio Grande River, and there's a treaty between Mexico and the U.S. The boundary between the countries is at the river center line, and neither side can do anything to affect, to change the flow or alter the course of the Rio Grande River. And I think the criterion that was established was, 5% deflect, or 5% deflection. And so we had to analyze three miles of this fence that had 6-inch square bollards turned at 45 degrees to the channel, and they're 5 inches apart. And there's 3 miles of these things, and trying to figure out a way to model this. Some water went through the fence, but some was pushed out back into the river. And we worked with Gary Brunner, who was with HEC at the time. I think he's since left HEC. He basically gave us some advice as to how to do that, and we were actually able to reproduce the entire bollard fence with a variable 2D grid and connections and break lines and stuff, and able to do what I thought was really approximated a CFD, computational fluid dynamics model of the river. It was a very powerful, very interesting application. It took 70 hours to run on a pretty fast PC. But so that, we're kind of doing things, really kind of stretching the limits of what a 2D model was capable of.
So let me ask you a higher level question based on all of these case studies that you're thinking about now. And that is based on with all the attempts to use a model to actually support decision making, uh, can you categorize what has worked and what hasn't worked, and talk a little bit about that?
Oh boy. I think I'm kind of in the David Ford wrote a good editorial many years ago about models, the idea of using the simplest model consistent with the available data, and the need, the need for, what you're looking to solve for. Um, and so, the sort of the Occam's razor kind of thinking, the
Yep.
simplest is best if that gives you the answer you need. And so I'm a firm believer in that philosophy, and that's why I use Hack 5 a lot still, when there are certainly more powerful models. Um, in terms of operational models in particular, models like ResSim and Hack 5 even, or any kind of operational model, I think it's important to sort of minimize the complexity of the operating rules so that what the models generate will be reasonably representative of what actual operators can accomplish. In other words, by minimizing the number of decision variables and sources of errors and uncertainty, that I think that helps a lot, because models tend to, models have perfect information and perfect rule compliance. They tend to overstate the operational precision and the performance of reservoir systems. I think we found that out on the ACT compact negotiations, where the idea was to maintain a flow target is some distance downstream of two federal reservoirs in the ACT basin. And of course, the model could maintain it perfectly, given its simplified routing and at perfect knowledge of the system. But in real life, of course, a reservoir operator can't come anywhere close to that. And they're always going to, if there's a minimum flow required, they're going to release more than that minimum flow. And that over release is going to cause the performance of the system it's going to degrade it in comparison to what the model would predict. So, that's I think it's I think the idea of keeping it simple is, I guess, if there's one thing I would, I guess a watchword I would say, that would be the key, is to keep things as simple as possible.
Okay, thanks. Let me come at you in an orthogonal direction now. We think of modelers as coders, um, working alone, deeply focused on small details, and yet you and I both know that stakeholder participation is really important. How has stakeholder participation changed your process as a modeler, um, and changed modeling in general?
Well, like you said, it's working alone is a lot easier, but uh, there definitely there's some good and some I'd say obstacles, or there's some challenges, I guess, posed by stakeholder involvement. Um, First of all, stakeholder buy-in is essential, and so without that, of course, there won't be a solution, or if there is a solution, it'll end up in litigation at some point in time. But even with stakeholder buy-in, sometimes it's not enough. Sometimes outside interest can overrule an agreement between the parties. And I'd say an example of that is we had an ACT allocation formula agreement between Georgia and Alabama in I think it was 2002. And the two states agreed on it, and all the modelers and the stakeholders involved at the time agreed upon it. But it was undermined and eventually stopped, or eventually, well, there's a couple things happened. New governors got elected, and they, that changed things. But also it was opposed, I guess, to some extent by the federal power customers because of the way the power generation rules were incorporated in the allocation formula. So that, stakeholder participation is essential, but it's not necessarily sufficient. The other thing is it's really critical to involve the right stakeholders. I mean, stakeholders should not just be an unorganized, collection of parties that don't necessarily represent core issues that are under negotiation. In other words, if there's ancillary issues or non-negotiable, issues that are for which water is a proxy, for example, I don't know. I'm trying to think of, well, certainly ideologies are non-negotiable. Membership in a group or classes, or those things are not negotiable. So sometimes you have to be careful to involve the right stakeholders, the ones that actually can represent and are open-minded and can authoritatively represent different interests in the solution. So there has to be some sort of institutional organization to the stakeholder groups.
Okay. Thank you for that trip into a related subject. Let's get back to modeling. We know that models don't exist in a vacuum, that they're part of a process including data acquisition, interpretation. Let me ask you, for the modeling tools that you've used or been involved with, what are the technical or process-related modeling enhancements you think would most improve water resources planning?
Well, I think getting back to sort of the theme of simplification, maybe simplified and more intuitive model setup capabilities. Same thing with post-processing and analysis of simulation results would be that makes it more accessible, I guess, to stakeholders and to modelers as well. I mean, we all do better if things are simpler. I also think it's probably going to. I think it's going to be important increasingly in the future to standardize platforms for software or for model integration. Kind of plug and play software like I mentioned Delfuse and HEC Watt and HEC RTS, so that basically it'd be relatively easy for any modeler, even a non-expert in a particular area, to pull different models that have been, for example, if an HEC HMS model has been developed in a watershed and an HEC RAS model has been developed, and they want to look at, changing the operation of a dam or something, to be able to pull different models together, including more models and all this kind of stuff, into an integrated system and have all these models talk to each other, more easily. I think that seems to be where things are going.
Okay, thanks.
One other thing I was going to add to that, there's a lot of attention to looking at climate effects on hydrology and reservoir operations. I think it would be nice to have a kind of a library, I guess, of downscaled hydrologic databases or pre-programmed kind of local climate effects hydrology adjustments that you could pull from to run these models, so that it's because everybody does things differently, I guess, nowadays. And it would be kind of nice to have kind of a standardized so climate adjusted databases.
Let me use that as a platform to spring into just the opposite mode. Rather than the best standardized, useful to everybody applications, just for fun, can you talk about the most interesting or unusual modeling applications that you've encountered in your 50 years of doing this?
Yeah, actually the most interesting one was It was a Lake Winnipeg regulation model. It was a model developed by Manitoba Hydro to simulate, the plan for operational planning of Lake Winnipeg and hydropower projects stations on the Nelson and Churchill River basins in Manitoba province. There in Manitoba, basically about 95+% of all power needs in Manitoba province are supplied by hydropower. There's a lot of exchange, exports and imports of power into the U.S. grid as well, and there's a lot of environmental and physical constraints in operating this system beyond what we normally think of in terms of the hydropower system. For example, they have frazzle ice management is a very important component. In other words, preventing frazzle ice formation in the fall and early winter. There's a requirement to cut back releases from the hydropower stations, from the power stations, to allow formation of a sheet of ice over the river so they can discharge water underneath and continue to generate to meet the needs of the power grid. Well, the operating rules are so complex and so I guess not what do you call it, variable, that the operators of the system. I was involved in reviewing the license application, and the model that they used, and they actually, we had a 2-day kind of indoctrination to this model. It was really kind of amazing. They couldn't reduce the operating rules to a fixed rule base that they could put in a model like RESM or something like that. So they had developed this interactive simulation model where they had 2 spreadsheet models that were doing the water balance accounting in the 2 different river basins, and they had 2 other spreadsheet models that routed the releases and inflows and stuff through the system. But the actual release decisions were made by basically a panel of operators would basically sit down and kind of by trial and error determine what they would release, and they test that, and then they would compare what they came up with what they actually did if they were simulating using historical data. And so it was kind of an interactive, a living model. It was very interesting, and I'm not sure today if there's a model capable of reducing their operational considerations to a fixed rule base. So that, I think that was one of the more interesting ones I've seen.
Very interesting.
Yeah.
So at the point in your career, you probably get asked by younger people for advice. Could you tell me a little bit about the kind of advice they ask for and the kind of advice that you would offer somebody just starting out as a water resources modeler?
I'd say not to see the model as a means to an end, not the end. And the idea is not to force fit a certain model to a certain application. It's really important to recognize model limitations, especially in interpreting model results. The model complexity should be consistent with the available data and the needed accuracy of the outputs of decision variables. I would say it's good to engage actual water managers. Now, I'm talking about in terms of reservoir system models or river system models. It would be good to engage experienced operators in the design and review of the model, because there's a tendency with, we have models that can do things that can't be done in real life, and there's a tendency to be a little bit too cute, I guess, or too tricky, I guess, in terms of formulating solutions. But I think it's good to have kind of an anchor or of balancing influence and saying what's realistic, what's practical, and what isn't. So so don't just model some things that you can't actually put into practice. I mentioned before about engaging the right stakeholders in conflict management processes. I think that's really important. It's not just stakeholder engagement, but it's getting the right stakeholders involved.
So that's a good segue to my last question. You and I take for granted that when there are questions about how to manage water, that models are involved, um, and uh, and yet we both have been in public areas where the public is um, not well informed about these things, and there's surrounding uncertainty about the uh, honesty and competitive compatibility of government decisions with the facts. Um, if someone not in our field were to ask you about it, what advice would you offer them? What would you tell them about what we do?
Well, I would say rather than trying to accommodate what they're asking to do is an uninformed or poorly informed, or just somebody who is not an expert in this field. I would the thing I would do basically I would encourage them to learn as much about it as possible, and in doing so, they might then also come to trust more, to believe more in what we're doing. I don't think you can ever, if the models and everything remain a black box to people, I don't know that you're ever going to be able to convince them that they're right, except to encourage them to learn about it and to and offer to explain as much as answer their questions and all. But I think knowledge is power, and I think it's the best way is to encourage them to learn. If they're not in our field, to learn as much about it as they can.
Okay,